We will now find the volume of a pyramid of the base S times S and the height H. To do this, we will slice the pyramid, which is the solid, horizontally so that we obtain the cross-section in the shape of the square. We label this square x by x. This is only a representative square. It should be x sub I. The area of the cross-section is x sub I squared, so the volume of the slice is x sub I squared times delta y, which is the thickness. In this case, we position the top of the pyramid at the origin with the positive y-axis pointing downward. The cross-section had the thickness of delta y. We then use similar triangles to express x in terms of y. The distance from the origin to the slice is y sub I. And so using similar triangles, we have x sub I over yi equals s over h. X sub I is therefore yi times s over h. The volume of a representative slice is y sub I s over h squared times delta y. Simplifying this, we have s squared over h squared yi squared delta y. As n goes to infinity, we obtain the definite integral from a to b of s squared over h squared times y squared dy, where s and h are fixed, so we can bring s squared over h squared to the front of the definite integral. The lower limit of integration is 0 and the upper limit of integration is h because the slices lie between y equals 0 and y equals h. The integrand is y squared dy. To evaluate the definite integral, we would first find the antiderivative of y squared, which is 1/3 y cubed, and we keep the constant s squared over h squared. Evaluate it at 0 and h. Plug in h, we have s squared over h squared times h cubed over 3 minus, plug in 0, we have s squared over h squared times 0 cubed over 3. But the second term is 0. And so we end up with s squared times h over 3. This is 1/3 s squared times h. This implies that if we have a pyramid whose base is the square s and whose height is h, then the volume is 1/3 s squared times h.